So again, in the packet, page 107. Are we all there? We got it. Page 107. We're looking at number 3 to start with. So, and you can write this in the packet if you write really small. If you don't write small, you could write it on the same sheet you have your warm-up on, or you could add it to the notes from last night. Wherever you write it is okay with me. So what I'm going to do first is I just want to recognize what the different transformations are. So we've got some sort of function. They're just saying that the parent function, when they write f of x as the parent function, and they don't actually tell you what the parent function is, it means they made it up. So this is not a quadratic. It's not an absolute value graph. It's not a square root graph. They made up a graph that looks like a rectangle, and they're calling that the parent function. All right, so that's what they mean. Anytime they say the parent function is y equals f of x, it means they made up a shape, and they're calling it the parent graph, and they're asking you to transform it. So for this one, we have a rectangle, and then we want to see what transformations we're doing to that rectangle. So what does a 2 in the very front mean? Stretch. What kind of stretch? Vertical. Okay, so my first transformation is vertical stretch by 2. And that's on the outside of the function. That's what we learned yesterday, is if we have a number in front of the equation, that could be reflect over x or vertical stretch or compression, right? The other 1/2 is in front of the x, but it's inside the function, so that means it's horizontal. This is new. This is what we learned in the video last night. So if we recall, anything that happens inside the function is always the opposite of what we would think. So when I look at that, I think compression. So the opposite of that would be what? Stretch. So this is a horizontal stretch. And then to figure out what the number is, we just flip the fraction. So if you flip that, what do you get? 2. Right. And what's it called when you flip a fraction? Reciprocal. All right. So it means you found the reciprocal of the fraction when you flip it. Okay. So we have a vertical stretch of 2, a horizontal stretch of 2, and then what's the number minus 2 on the end? Down 2. And I know that it's down because it's on the end. If it was left or right, it'd be inside. Okay, so down 2. All right, so one thing you might have picked up on, but you might not have picked up on, is that the stuff on the outside of the function happens to the y. The stuff on the inside of the function happens to the x. All right, so that's an easy way to kind of differentiate between the two. Outside happens to y, inside happens to x. So what we're going to do next is, since we're not given a table for this parent function, we go ahead and we make one ourselves. So we're going to figure out some key points that when we find those points and transform them, we can then draw the new graph. And there's not a rule to how many points you have to find. I typically go for the bare minimum. So with this one, there's 4 corners. I could do 4. If you wanted to get real crazy, you could add like these middle ones in too, and maybe a middle one in there, and then you'd have to transform all those points. And that just doesn't sound fun to me, so I'm only going to do 4. Does that make sense? So you just pick as many as you need to be able to do the shape accurately. Okay, so for some people that's more, for some people that's less. All right, so for this one, if I'm just using the corners, that means I've got the point -4, +4. I have the point -2, +4. I have the point, not -2, -1. Nobody corrected me, guys. You're supposed to be like, Miss Rice. Come on, man. All right, -1, -2. And then the last one, -4, -2. Okay, did I write any down wrong?
No.
No? Okay. All right. And then typically I do my transformations in order. It doesn't matter as long as you do the first two first. Anything that multiplies has to happen before the stuff that adds or subtracts. So if I'm doing a vertical stretch, that's outside the function, so it happens to the y value. So I'm going to take all of the y values, and what am I going to do? Times 2. So keep the x the same, multiply by 2. Keep the x the same, multiply by 2. So I did a vertical stretch of 2, and so I multiplied y by 2. So next we have a horizontal stretch. What do I do now? Times 2 with the x, all right? So a horizontal stretch is inside the function. That means it happens to x. So I'm going to take all the x values and multiply the x values by 2. So -8, keep the y the same. -2, keep the y the same. So I did a horizontal stretch of 2, I multiplied the x by 2. All right, and then my last transformation is down to, how do I do that? -2 from the y, and I know it's the y because it's outside of the function. So anything outside of the function always happens to y. So I'm going to say keep my x the same and -2. Keep my x the same, -2. Keep my x the same, -2. Keep my x the same, -2. All right, and then to make sure that our chart makes sense, we're going to take those points and graph them. So when you graph them, you should see a rectangle that has moved down and is twice as tall and twice as wide as the original rectangle was. So I have the point -8, +6, -2, +6, -2, -6, and then -8, -6. And if you graph that, it's definitely bigger than the original. All right, it's kind of hard to see on here. Wasn't that fun? Yeah. Oh man, love me some math class. No? Okay. Tough crowd. All right, which one would you guys like to do next? All of them are equally easy? What about number 1? Look at number 1. What's weird about number 1? It's got 2 sides. What else is weird about number 1? What do you see about the x? Yeah, most of the stuff is going to happen to the x, right? Because it's mostly inside. And then what do we see about the x inside? It's got a 2 in front of it, right? It's got a compression. Yeah, good recognition there. The thing that's weird about number 1 is that you're not allowed to work with them while they're like this. Anyone remember what we have to do to problems like this? We have to factor it. So I'm going to rewrite this problem so I don't get my transformations wrong. So I need the x to be all by itself. And to do that, what do I do with the 2? I factor it out like a GCF. So if I take out the 2, what's left over? 2. So +2. So if I looked at the original problem, I might think that it's left 4, but that would be wrong. It's actually left 2, and I can only see that once I factor it out. Okay. So I am not working with this one. I'm working with this one. This is a very commonly missed question on the NCFE, where it's like a super easy question, just like recognize what the transformations are, and students, I think it was like only 25% of students got it right because they forgot to factor it. So it's not hard, it's just something that's easy to forget. So you want to make sure you watch out for that because it will throw everything else off. All right, so our transformations are what? Okay, the negative in the front is reflect over the x-axis. The 2 inside, we already said was a compression, but is it horizontal or is it vertical? Horizontal. And it looks like a stretch if you just look at it, and that's why we know it's a compression, because it's inside, so it's the opposite of what we would think. So 2 inside means compression, and then here we have a +2, which means what? Yeah, so we're going to say left 2, which means we're going to be subtracting 2. All right, there's our transformations. And then here, we just have to pick enough points so we can draw the picture. So I'm going to do the end points and then that corner right there. And then I'm going to write them down. I'm going to give them letters. I do this sometimes when I think that maybe after I transform it, I'll have a hard idea knowing which points to connect. So if I give them letters, sometimes it helps me to know what order to connect them, and then I feel better about it. So A is -2, +2. B is +3, +4. C is 6, -3. And if you hate writing the letters, you don't have to. It's not required. It can just help. Okay. So what should we do? Okay, so we're going to take the y coordinates and we're going to multiply them by -1. So we're changing the signs. So we've got 3, -4, 6, 3. If the charts have been fairly easy for you, you can ignore me and just continue working. I will not be offended. Okay, but I know that for some people there's been a little bit of a struggle. All right. Horizontal compression means do what? Is it to the x or to the y?
To the x.
To the x, and what are we going to do? Yeah, so we're going to take all the x values and we're going to multiply them by 1/2. So we've got 1/2 of -2, 1/2 of 3, 1/2 of 6. You don't have to write these words down here at the bottom every time. I'm writing that so that if you need it in your notes, then you'll have it to write down. Okay, and then last, what should we do? Subtract 2. So each of the x's will -2. What's 1.5 minus 2? -1/2. 1. Okay. And then these are the points that we're going to go ahead and graph. That much fun? No? You guys are like very stressed out sounding with your sighs. Okay, should look like that. So it's definitely not as wide as it used to be, right? Because it got horizontally compressed, so it got squished sideways. And then the top of it reflected over, so that's why the point is down instead of up. And then I just made sure that I drew my points in the same order that I wrote them down in, so I knew what order to connect them. Okay. We good? All right. What I want you to do is I want you for number 2 to write down the different transformations you have so we can make sure that we have those down. Mm-hmm.
Like you just, I know it's a horizontal stretch, but do you just do it?
This one's actually it's not a horizontal stretch. It looks like a stretch. So it's a horizontal compression.
Okay,
So instead of using 2, what are we going to use?
1/2.
1/2.
But
And you're gonna keep the negative with it.
Okay.
Yeah. So we have the negative inside. It still means reflect, but what are you reflecting over? You're using the 1/2 as well, but what are you reflecting over? The y-axis. So inside we have reflect over the y-axis and a compression of 1/2, a horizontal compression of 1/2. So if you want to do both of those transformations at the same time, you can just take your x value and multiply it by negative 1/2. And that would take care of the reflection and it would take care of the compression.
So can you repeat why you reflect over the y again?
Because it's inside. So when you reflect over the y-axis, you take something that was on the left and you move it to the right. And since that's a left and a right thing that's happening, that means it happens to the x coordinate. So you're taking, to do the negative, the reflection over y, you're going to multiply your x coordinate by a negative. And then to do the 2, that's a horizontal compression of 1/2. And you would multiply your x values by 1/2. So if you want to do them at the same time, you could just take the x value and multiply it by negative 1/2. And then you would take care of both of those transformations at the same time. What are the transformations in the front?
Reflect over x and the half of y.
So reflect over x, and what's half of y mean? What's the transformation? Compression, vertical compression. So we have reflect over x and vertical compression. And if you wanted to do both of those at the same time, you would take the y coordinate and multiply it by negative 1/2. So in this problem, coincidentally, you're doing the same thing to the x coordinate and the y coordinate. You're going to multiply them both by negative 1/2. Okay. So I'm going to go ahead and just write down all those things so that we have them. How many points are you guys going to write down to do this one? You should probably write down 4. So I've got like the ends and then the places where it switches direction. All right. Hold on, come on. There. All right, so we're gonna multiply y by negative 1/2 and multiply x by negative 1/2. Okay. Now for 4, I think if you guys could do the other 3 problems, you can definitely do 4, but make sure that when you are figuring out your points, you're for sure going to need the end point, and you're for sure going to need this one. But then for this last part, a lot of students don't know how many points they should do to get the whole shape. So what I did is I did the beginning of the half circle and the end of the half circle, so I would know that that's what the half circle was. But then I also did this point too, so I would know where the curve happened to be. So when I did this one, I did 5 points, and I found that was enough to feel relatively okay about drawing it. All right. So for right now, your job is to finish the to finish 3 and 4 on this so that page 107 is completely done. Okay? Reasonable? Yes, we can do it. All right. If you look at the front of the packet, you can see I typed up everything for you. So all of the transformations are written over here so you can see exactly what everything means. And then how to do those transformations is written over here. All right, so you should have it written in your notes because it's something I've been talking about in the videos that you've been writing down, but you also have it written on the front of here. I want to add a little bit more to this. So this is that notation of like a parent function that doesn't match a specific parent graph. This is just like I made up a parent function and it's like a shape of something. So I'm gonna write here we're going to say that the A and the C value are always things that you multiply. So those are your stretches and your compressions and your reflections. And so whatever those numbers happen to be, you always multiply them by the X or the Y. And then the H and the K, those are always things you add or subtract. I don't know what I'm trying to do with that arrow. I'm going to fix that. But those are things you add or subtract because you're moving left, right, or up, down. Okay, and then the other part is what I was saying while we were doing those last couple problems, is that anything that happens on the inside happens to the X's, and anything that happens on the outside happens to the Y's. So for those of you who like to see something visually, that's like the visual of how the equations work. Okay, inside X's, outside's Y's. The first two are multiplication, the second two are addition and subtraction. So one of the things I said in last night's video is that the transformations that involve multiplication have to come first, and then the ones that involve addition and subtraction come second. That's why it works if you just do your transformations from left to right. It will work every time. And that's why I've typically done it that way in the video, is because then it's your natural inclination to just do it from left to right, and you'll always get it right. Okay, does that make sense? Mm-hmm. Okay, so what I want you to do next is I'm going to help you guys look at these and just make sure we have the right function that we're looking at to start with. So when you finish the other packet, page 107, you're going to start doing the evens on this packet, and it's just like yesterday. We're still going to take the table of values, and we're going to write it down, and we're still going to find the vertex, and we're still going to find the domain and range. We're going to do all the things we did yesterday. Okay? We're just doing it for functions that have transformations that we learned about last night. So this one, when it's written like this, I have to factor it because my X is supposed to be alone. And my X has a negative in front of it right now. So this is not the version I'm going to look at for my transformations. I'm going to rewrite it as a factored form, and that's the version I'm going to look at for my transformations. So what is it that I have to take out? The negative, -1. So I'm going to put a negative in the front, or you could put a -1 if you want. And when I divide out that negative, I get an X, and what else do I get? -4. So this function has the transformations reflect over the y-axis and move to the right 4. Okay? There's no number on the end, you'll notice, and so that means that if there was a number, you would put 0 plus 0 on the end. So if we wanted to know the vertex for this, we can still use that shortcut we used yesterday. We're going to do the opposite of this number and then use this number. So our vertex would be 4, 0. All right, so number 2 is ready to go. We're going to flip to number 4. Do you guys want to write this as a decimal, or do you want to think of it as a fraction 1/2? Fraction? Okay. So when I write this, I'm going to switch the form because I know that X is supposed to be alone. And I've got everything as being squared, but I have to take that 1/2 out that was in front of the X. And I think for any of the problems that are written as decimals, fractions are probably good because we do often flip them. So it's easier to flip a fraction than a decimal. So I'm keeping everything the same, I'm just factoring out that 1/2. And if you take a 3 and you divide it by 1/2, you're trying to see how many halves are in 3. And what would that be? It'd be 6. Yeah. 3 divided by 1/2 is actually 6. So when you divide by fractions that are smaller than 1, when you divide by those decimals, it makes the number bigger, not smaller. Okay, so 3 divided by 1/2 is actually 6. And then this form is ready for you to do the transformations with. What would the vertex be for this one? 6, -1. Okay. So the vertex here is 6, -1. All right. Number 6 is ready to go that way. If you don't like the 0.75, what could you replace it with? 3/4. Okay. Be careful of this one because when I did this problem, I said that's a horizontal compression of 3/4. And was I right? No, because what is it? It's a horizontal stretch of 4/3. So that might be a good one to write down because we might have missed it. So I did it wrong at first because I wasn't thinking. We get so used to working with the fractions that have a 1 in them that sometimes we forget to mess with the fractions that have something other than 1. So that one would be a horizontal stretch of 4/3. Okay? Because we got to flip it. All right, number 8. Is number 8 ready to work with? No. So we got to fix this one as well. I'm going to keep the -5 in the very front. And what should I have inside? X plus 3. And what should go in front? 2. Are you guys okay with recognizing what's considered inside and what's considered outside?
Yeah.
Yeah? We're okay with that? Okay. So on this one, the -5 is outside, the -2 is outside, and then all that stuff is considered to be inside. Okay. Let's look at 10. Is this one ready to go? Nope, so we got to fix this one as well. That's not just a 1/3, I have a negative sign in front of that. Okay, so if I take 2 and I divide it by a negative, I'm going to get a negative, so I know that should be a minus. 2 divided by 1/3, I'm asking myself how many 1/3s are in 2. 6. There's 6 of them. 1/3 goes into 2 6 times. So that should be -6. Okay. Makes sense? We did fix that? Okay. So at this point, all those are ready to go. You just have to start with the table that we use for the individual parent function. And now you're doing exactly what you did yesterday. You're doing the transformations. You're drawing the picture of the graph. You're finding the locator point, the domain, the range. Okay? All right.